Hello everyone. In this video I'm going to talk about related samples t-tests along with effect sizes and confidence intervals for these types of designs. So before we start talking about the 4 pillars of scientific reasoning, what we first need to talk about a bit is related measures designs and what they are, and then we'll relate that information to these 4 pillars of scientific reasoning. The first thing we need to deal with is what is a related measures design? And there are 2 broad categories of these types of designs. The first one is a simple pre-test, post-test design where you're going to measure the same people twice, right? And so one way you can do that is give people a pre-test on some variable, like it could be their cholesterol levels, and then give them a treatment, right? A drug that's meant to lower their cholesterol levels, and then give these same people a post-test, right? That would be a pre-test, post-test design. So for example, say that I'm interested in the effects of yoga and walking on people's stress levels. I have 2 conditions, yoga and walking. I could have people in condition 1 walk and then measure their stress levels, and then I could have the same people do yoga and measure their stress levels after they do yoga, right? However, we might find that stress levels are different in those 2 different times just because of the passage of time. And so what we would do is counterbalance typically in this type of research, where half of the people start with condition 1 and the other people start with condition 2, and then they flip-flop the second time. Either way, the data is analyzed the same way. When you have the same people measured twice, you're going to use a related measures t-test. You can also use a related measures t-test when you match people on some pre-existing variables, and then you treat them as if they're the same person. So for an example, we're looking at people here with pre-existing cholesterol levels. And what I do is I match them up with somebody else with the same pre-existing cholesterol level, right? So I have, for example, this person here has a cholesterol level of 240. This other person has a cholesterol level of 240. I randomly assign them to one of these 2 conditions, right? So in this case, this person, the blue person, received a drug. The red person received a placebo. And then we measure their cholesterol levels, right? But we treat them as if they're the same person for analysis purposes because they're matched on that pre-existing cholesterol level. And the whole study then would consist of pairs of people. Here I have this orange person who has a cholesterol level of 280 matched up with this other person with a cholesterol level of 280. Randomly assign them, one person gets the drug, one person gets the placebo, and then measure their cholesterol levels. Okay? So that's a match design, and we find that these are pretty hard to do in terms of finding people who you can match up on pre-existing variables, but when you do them, you can use a repeated measures t-test or related measures t-test. One of the most common ways you see people doing match designs is using twins. So if you have twins, identical twins in particular, they're matched on like genetics and environment often, and so they randomly select one twin to be in one condition and another twin to be in another condition in a study. And that would be a match design, and the data are analyzed in exactly the same way as they are for any other related measures design. The example we're going to work with in this video is, does meditation reduce people's perceptions of their stress levels? So research has actually revealed pretty mixed evidence on the effectiveness of meditation for reducing stress. And so a researcher wonders if regular reminders would be helpful. And so they develop a phone app that reminds people to meditate twice a day for 5 minutes each time, and they provide a daily guided meditation practice. So to determine if this app is effective, the researcher recruits 121 people to participate in the study, and all participants complete a survey that measures their perceived stress at the beginning of the study. They use the app for 1 month. At the end of the month, they again complete the exact same perceived stress survey. So what we want to do is use the 4 pillars of scientific reasoning to determine if people can reduce their stress levels by using this app. Our dependent measure in this study is perceived stress. And so to measure that, we're using this perceived stress scale, where people respond to 10 different questions and they make ratings on a scale from 0, which is never, to 4, very often. Right? So when people sum up these 10 items, they get a score between 0 and 40. And we typically consider variables like this when you're summing up basically ordinal data. We still consider it to be interval data for the purposes of our analyses. So we can go ahead and compute means for those scale scores. So we're going to use the 4 pillars of scientific reasoning to investigate this question of whether or not the app actually helps reduce people's perceived stress levels. And as a reminder, we have statistical evidence and scientific context to consider. So there are 3 different pillars that address statistical evidence. We have hypothesis testing with continuous p-values, assessing practical importance with effect sizes, and also population estimation with confidence intervals. Those all provide statistical evidence for us to think about when we're interpreting our data. Now we also need to remember that data doesn't occur by itself. It needs to take place within a scientific context. And so we also need to consider the 4th pillar here, which is the methodology, how rigorous the research methodology was, and also the scientific literature. And that is, how does this particular study fit in with the existing scientific literature? Our first pillar, hypothesis testing with continuous p-values, has the largest number of steps. So we're starting here with the first pillar. There are 5 different steps we're going to use when we're hypothesis testing with continuous p-values, starting with choosing the correct statistic. You can use the related samples t-test when you either have measured the same people twice or you have matched people on some pre-existing variable. In this case, we've measured the same people twice. We're giving them a pretest, and then we're asking them to meditate using this app for a month, and then we use a post-test. We're going to compute means for these 2 groups because the perceived stress scale is measured on an interval ratio scale. Our second step is to determine if the statistical assumptions of the test are met. So all tests have statistical assumptions, and if these assumptions are violated, the results might be misleading. And so we need to be careful to make sure that these assumptions have been met. Okay. So there are 3 that we need to consider for the related samples T. One is independence, the other is appropriate measurement, and the last one is the normality of the distributions. The independence assumption is that each participant score within a given condition is independent of all other participant scores within that same condition. So if we're looking at pre-test scores, each person's score needs to be independent of other people's score within that treatment condition. Likewise, when we look at post-test scores, each person's score needs to be independent of every other person's score at the post-test time. Now we know that the data are not independent between conditions because it's the same people measured twice. That's not the assumption. The assumption is that within conditions, each person's responses are independent of everybody else's. Everybody responds in their own way without talking with each other, looking at each other's work, or something like that. Our next assumption is appropriate measurement, and that means that our dependent measure, stress, has to be measured on an interval ratio scale, which we already established. You can't compute a mean unless you have an interval ratio scale. And then finally, we have the normality of distributions assumption, and this is that the distribution of sample means must be normally distributed. This isn't about the scores, so our temptation is often to plot the scores from our data set to see if they're normally distributed. And that's not the assumption. Our assumption is that the distribution of sample means is normally distributed, and that's going to be true according to the central limit theorem, either if our sample size is close to 30 or higher, or if the population of scores is normally distributed. In this case, we have a big sample size of 121 people, and so we're confident moving forward that our distribution of sample means will be normally distributed. The next thing we need to do in step 3 is identify the null hypothesis. And the null hypothesis is telling us what the population parameters would be if there were no effect in the population. Or in this case, that the meditating for 1 month using the app has no effect on people's stress levels. If that were the case, then we would find no difference between the pretest scores and the post-test scores. Or another way of thinking about this is that the difference scores, the mean of the different scores, it's abbreviated mu sub d for different scores. So the population mean of the different scores would be equal to 0 because people's scores on average wouldn't change when they use the app. Okay. Now you'll note here that we are doing a two-tailed test. We're not specifying a direction. We're not saying if scores will go up or go down, because either would be interesting, right? It's interesting to know if scores on stress go up after using the app. Maybe being reminded feels like they're pestering you and you're actually increasing your stress. Or it would also be interesting if scores went down and the app actually effectively reduced stress. So for that reason, we are going to do a two-tailed test. Now the fourth step is to graph our sample data, and what we're doing here is looking to see what our data look like before we start jumping into numbers, thinking about it a little bit, and also just checking for any weirdness in your data, right? So I can look here and see that my pretest stress scores are higher than my post-test stress scores, right? This dot here is the mean, which is higher than the post-test scores. You can also see that the medians are lower than the means, which suggests we have skewed distributions of scores, which is okay, because remember our assumption isn't about the scores, it's about the distribution of sample means. Right? So your particular output may look a little bit different than mine. This one I generated with Jamovi, but your goal is to look and see, like, yeah, it looks like scores are higher on the pre-test than the post-test. I don't see any outliers in my graph because these graphs would typically show you the outliers as well. Just start thinking about your data before you start computing things. Our next step is to compute the t and the p-value. And also we're going to compute descriptive statistics along the way. So we have the mean and the standard deviations for the pre-test and the post-test. We can see that the mean at the pre-test is 18.388, the post-test is 16.02, and what we want to know is that mean difference big enough for us to think that that difference is not just due to sampling error? So to figure this out, we compute a t-statistic, and the t is the difference between the means, the observed difference between the sample means, divided by the estimated standard error of the mean difference. Our mean difference is 2.364, which is just the difference between the 18.39 and 16.02 here. The standard error of the mean difference is down here, the standard error of the difference scores. Okay? It's the estimated standard error, and that's 0.921. So we're taking an observed difference divided by the difference we'd expect just due to sampling error. So the bigger our t, the more confident we are that the results are not due to sampling error. In this case, our t is 2.57. Okay? The other thing to note here is that the degrees of freedom for this test are equal to 120, which is n-1, noting that this is the number of people in the study, or the number of pairs of scores in the study. Once you have your t, you also get the p-value from the output. So our p-value here is 0.01. What I've graphed here is a distribution of sample means, assuming that the null hypothesis is true. The mean of that distribution is equal to 0. We're looking at t-scores here. So I graphed the t of 2.57 and also a t of less than negative 2.57. Now the p-value is the probability of getting a value in either of these tails if the null hypothesis is true. So if I were to take a sample of 121 people from the population, what's the probability that I would get a t as extreme as the one I obtained or more extreme if in fact the null is true and the treatment really has no impact on people's stress levels? In this case, our p-value is 0.01, which is a very small probability that I would pull that sample just due to sampling error, or to pull a sample mean that extreme just due to sampling error. So here we have a p-value of 0.01, and this is an outcome that's really unlikely if the null hypothesis is true, right? Basically, there's a 1% chance we would get a t as extreme or more extreme than the one we obtained if in fact the null is true. So this suggests that scores did in fact decrease after using the meditation app. That difference is unlikely to be due to sampling error. Now, whether or not we can conclude that it's actually due to the treatment is another story. We're going to come back to this. All we can say right now, based on this information, is that our P is low, and it's pretty strong evidence against the null hypothesis. Also, remember that when we work with p-values, they are meant to be interpreted continuously, not with hard and fast rules. They're just one piece of information to help you think about your data. So these are helpful guidelines to give you sort of verbal interpretations when you're thinking about your data here. The p-value tells us that these results are unlikely to be due to sampling error. Now, the next step is to figure out, well, how big of an effect did this app or did this treatment actually have on people's stress levels? And does it have practical importance? To answer that question, we're going to start by computing effect sizes. So there are a couple of different ways you can look at effect sizes to determine how large of an effect you're looking at. One thing you can do is just look at this in raw score units. Right? Our scale ranged from 0 to 40, right? 0 meaning the least amount of stress, 40 being the most amount of stress, and our mean difference was 2.36. So on a 40-point scale, the app improved people's stress levels by 2.36. Now, whether or not that's a big enough change for you depends on, your knowledge and understanding of the literature. Right? So I realize right now that you don't have a lot of background here, but I can say with a lot of certainty here that on a 40-point scale, a change of 2.3 isn't a ton. All right, now you can also compute an effect size as a standardized effect size D. The D we're using here is the difference, the mean of the different scores divided by the standard deviation of the different scores, which gives you a D of 0.23, which you can get from the output of many statistical programs. And here we have Cohen's D from Jamovi is what I used to generate it at 0.23. Jamovi, interestingly, does not give you the standard deviation of the different scores. I had to generate this myself. You just get it by taking the standard error of the mean of the different scores and multiplying it by the square root of n to get that. Not all programs give D, but those that do often give this version of D. There are other ways to compute D. Some people actually, or an effect size, some people use G, which is the observed deviation, just like we have here in the numerator, but the denominator they use is the average of the standard deviations between the two groups. We're going to focus on this D rather than G in the class, and so I'm not going to go into detail with that here, but there's another video explaining that particular issue. Now, the advantage of using standardized effect sizes is that they allow you to compare effect sizes across studies with different measures of stress. Right? So you could imagine that if one researcher had used this same stress scale that we used, you could compare raw scores across studies. But if somebody had used a different measure of stress, we'd need to put them into the same units, and we do that by doing D. Now, in terms of interpreting D, we look at the absolute value of D, and a D of 0.23, according to these guidelines, would be considered a small effect. Okay. All right, so we've worked through the first two pillars. We now have a p-value, and we know that the difference we observed is unlikely to be due to sampling error. And in terms of effect size, we know that we have a small effect. And next we want to look at our confidence intervals, and this is going to give us an estimate of how precise our estimate is of the population parameters in terms of the mean differences there. So our sample mean difference gives us an estimate of the actual difference between stress levels before and using the meditation app in the population. Now, if we want to know how precise that one estimate that we have is, we can compute a confidence interval around the raw score mean difference. The formula we're going to use is we're going to take a point estimate, which is the mean of the different scores, and then we're going to add or subtract the margin of error to that. And the margin of error is the t for the confidence interval multiplied by the standard error of the mean difference. I'm not going to go through the computations for the confidence intervals here. We did that in previous videos, in previous chapters. right now we're just getting these confidence intervals from the output from statistical programs. The output I have here is from Jamovi, and it shows us the mean difference as well as the 95% confidence interval around that mean difference. Okay. So I can be 95% sure that the true mean difference in the population is somewhere between 0.5 and 4.18 in raw score units. You can also compute confidence intervals around the standardized effect size D using software. So here we have the confidence interval around our effect size. Our effect size is 0.23, and the 95% confidence interval has a lower bound of 0.05 and an upper bound of 0.41. So I'm 95% sure that the true effect size is somewhere between these two values. Or if I'm going to use verbal labels, it's somewhere between a negligible effect and a small to medium effect, right? So I'm 95% sure that the population effect size is between those two values. I think it also helps to look at this graphically, right? We can see here when we look at the confidence intervals on a graph that we have the one on the left is the 95% confidence intervals around the raw score, and the one on the right is the 95% confidence interval around the effect sizes. Right? What this points out to you is that those around the middle, right, are the more plausible options, right, than the ones out in the tails. So the outcomes in the middle are more likely or more plausible than the things out in the tails. Right? So although any of the values within the confidence interval are plausible, it's also the case that those closer to the middle, which are closer to our estimate from the sample, are more plausible than the ones in the tail. All right, so we've computed all of our statistics now. We have a p-value, we have assessed our practical importance with effect sizes, and we've also looked at our confidence intervals. Now we need to put this into a greater scientific context and consider the research methodology. We can start by considering the methodological rigor of the study. Was it a well-done study? Does the sample represent the population well? And things like that. We don't have information about whether the sample represents the population well. But one thing to consider in this study is we should consider the possibility that stress scores decreased for reasons other than just using the app, right? It's possible scores went down, but it's also possible that people's stress levels went down because of other things happening in their life, or it could have gone down because of just the expectation that they were being treated, even though the treatment wasn't really effective. It might have just been a placebo effect. So really, in these kinds of studies, what you'd like to see is a control group, and we did not have that here. Now, I realize you haven't necessarily taken research methods yet, and it's okay if that didn't come to you naturally in terms of understanding that, but we're just using this as an opportunity to introduce a little bit of research methodology into our discussions. Next, we have to determine how well the study fits into the scientific literature. So we'd said previously that previous research has shown sort of a mixed bag of results in terms of whether or not meditation helps reduce stress. Some have found that it does, some have found that it doesn't. Right? And to some extent, that depends on how they measure stress and what kind of interventions they're using. So what we're considering is what is the weight of the evidence? So we don't have a lot of knowledge here, but we can say that we have results here that suggest that our treatment was somewhat effective, right? It had a small effect, and it was unlikely to be due to sampling error. So this fits into and adds weight to the idea that maybe there is some evidence that using meditation could be helpful. Now, finally, what we need to do is pull this all together into a well-supported scientific conclusion that uses the statistical evidence from the three pillars and also considers the scientific context. When reporting our results, we're going to start with an APA-style summary statement. And this is a standard format that people use to report results across a variety of different journals, which makes it much easier to read journal articles if everybody's using the same basic format to present their results. So what we're starting with is by stating that we have done a related samples t-test, like letting the reader know what statistic we used. And we also computed effect sizes to compare stress scores before and after participants used the meditation app for 1 month. So the mean before and mean after, as well as the standard deviations, you can get them from the descriptive statistics table from your statistical output. Now for the t-statement, this t-statement looks a lot like, or exactly like, the t-statement from the single sample t. You report the degrees of freedom in parentheses, where the degrees of freedom is n-1. The t that you computed, you get that from your output. The p-value, which you also get from your output. The 95% confidence interval around the mean difference that you get right here. You get the effect size d from down here. And then finally you have the upper and lower bounds for the confidence interval down here. So in this part of the summary, all you're doing is giving the statistical results right now in that sentence. Next, we want to consider the research methodology and the scientific context. So I'm bringing back information from that initial slide where we talked about the idea that there's mixed evidence on the effectiveness of meditation for reducing stress, and then adding our study to this discussion. The results of our study suggest that the app may lead to small improvements in perceived stress, but we also want to mention that it's possible that something other than the app caused stress scores to decrease, and this study should really be replicated with a control group. Okay? Now note that in class examples or examples in the book, you won't always have knowledge of previous research or scientific methodology, and if that's the case, just say that you don't have that information. Just keep it as a placeholder so that when you do have more information, you remember to add it in. So we have our final scientific conclusion here. The first part is our results, where we have that original sentence where we just give all of the numbers and explain which statistics we used. And then I added another sentence giving a verbal summary of that. There's really no interpretation here, just a verbal summary. I'm just saying that scores were slightly lower after 1 month of using the app, and that difference is unlikely to be due to sampling error. Then finally, I give my summary of the previous research and how this study fits into that, and also talking about limitations and future directions. In a real paper, if you're writing this in APA-style paper, this section would go in the discussion section, right? It's not part of the results, but it's still important for us to consider as we're learning about statistics, rather than just trying to compute a bunch of numbers without putting them in any sort of context. These are just the references we used for to set up this problem. There's a lot of other research that you could pursue if you're really interested in the impact of meditation on stress or any other different dependent variables. All right, well, I hope that helps. In this video, our goal was just to go over the main points, the essential points of Chapter 5. There are other videos going into topics in more detail if you'd like a more nuanced discussion of it. And there are also other videos showing you how to run the analyses in different stats programs on our website. All right, so good luck.